We have studied the scheme of biasing the transistor at a constant current, where we sense the current difference at the drain and feed it back to the gate. Now we will study an alternative where we sense the current difference at the source and feed it back to the source. Okay. Then let's consider the transistor, and I'll place the current source down here because to sense at the source I will have to connect it to the source, so that's more convenient. The current ID in the MOS transistor flows from the drain to source. Since in this part we are not using the drain, that is, we sense at the source and feedback to the source, the drain can be connected to some fixed voltage. I'll assume that it's connected to the supply voltage VDD. Okay, later when we realize circuits using it, it'll have to be changed, but for now I'll concern myself with biasing and connect it to the supply voltage VDD. And because we are applying feedback to the source, the gate is connected to a fixed voltage. You can call it VG0. Okay. So now, first let's see what must happen. That is, we want ID to be equal to I0. Okay, and let me call this voltage as the source voltage Vs. Okay, please don't get confused between this and the signal source voltage. In this case we don't have a signal source, so there should be no confusion, but when you have both, don't get confused by that. We have this Vs, and then let's say ID happens to be more than I0. We want it to be equal to I0, so we have to reduce the value of ID. So what must happen to Vs? Please reason it out. Now ID must be reduced, which means that VGS must be reduced. Okay, obviously ID is an increasing function of VGS. If ID has to be reduced, VGS has to be reduced, and VGS itself equals VG0, which is fixed, minus Vs, which we can vary in this circuit. So this clearly means that Vs must be increased. Okay, so if the drain current of the transistor happens to be more than the desired current, then the source voltage must be increased. When you do this, the gate source voltage reduces and the current reduces. Okay, and exactly the opposite must be true when ID is smaller than I0. Vs must fall down so that the drain current increases. Okay, so this is the feedback action that we want. Now we generate the feedback action by comparing ID to I0. Okay, the current is flowing here from drain to source and the fixed current source is there, and to make the comparison we tie these two currents to the same node. Okay, just like before. Earlier we had connected the current source to the drain of the transistor, now we connect it to the source of the transistor. Okay, so we connect it up like that. If we do that, a difference ID minus I0 tends to flow out that way, and where does it go? It goes into the parasitic capacitor associated with that node. Okay, now what happens because of this connection? If ID is more than I0, okay, so that means that a current is being pumped into the capacitor like that. So Vs, which is the voltage across the capacitor in that polarity, Vs increases. Okay, and similarly, if ID is smaller than I0, then a current will be pulled out of the parasitic capacitor and the voltage starts falling down. Okay, so this happens just by virtue of connecting the current source to the source of the transistor. Okay, this happens because I0, the source, the current source is connected to the source of the transistor. Okay, Now you see that actually what we wanted for Vs, when ID is more than I0, we wanted Vs to increase, and that's already happening. Okay, so we don't even have to do anything. If we simply connect it up like that, if ID is more than I0, then this voltage will go on increasing. Okay, as it goes on increasing, VGS will go on decreasing and ID will go on decreasing. Similarly, if ID is less than I0, this voltage will keep on falling. VGS will go on increasing and the current will go on increasing. Okay, so simply connecting the current source to the source also completes the feedback action. Okay, and when does it reach steady state? That's when this current going into the parasitic capacitor 0, that is when ID equals I0. Okay, so in steady state, ID equals I0. So to bias the transistor in this way, to sense at the source and feedback to the source, we don't have to do anything. All we have to do is to connect the current source to the source of the transistor. Okay. Now why does this really work? The controlling part of the transistor current that is the gate source voltage. Okay, so this is between gate and source, and the controlled part, which is the drain current, that goes from drain to source, and you can clearly see that the source belongs to the controlled side as well as the controlling side of the transistor. Okay, the gate, you can only apply the input, it can only control, nothing will come out of the gate, it's not an output. Similarly, the drain, it's only an output, you can't apply something to the drain. Whereas source, it's common to both the controlling part and the controlled part. So that's why take a transistor, bias its gate at a fixed voltage and the drain also at a fixed voltage, VDD, and you just apply the current source I0 to the source, and it reaches steady state where ID equals I0. Okay, but still it's more useful to think of this circuit as having feedback. The feedback is internal to the transistor. Okay, that is, the source being part of both the control side and controlling side introduces feedback. So it's better if you think of this as a feedback circuit rather than as simply applying the current. That is, you connect the current source to the source terminal, and depending on the current difference, the source terminal goes up or down, and that action, the source voltage going up or down, will change the VGS and consequently change the current. So there is feedback in this simple circuit as well, although normally for feedback you assume that there is some circuit and there has to be a wire coming from the output to the input. That's our usual notion of feedback. Here the feedback is internal to the transistor. The source, being part of both the controlling and control side, accomplishes feedback, and this type of biasing naturally is known as source feedback bias. It's a very popular way of biasing the circuit. It's very simple and used quite a lot. Okay, and in the subsequent lessons we will look at how to realize amplifiers using this type of bias. Like I've said many times before, you can have many different kinds of bias circuits and many different kinds of functions. That is the incremental picture that we want to realize. Right now we know only one of them, that's the common source amplifier, but typically any function can be realized with any bias circuit. Okay, it's possible. Now of course some of them are more convenient than others, so they will be preferred, but you can have a variety of functions, variety of bias circuits, and a combination of biasing and the realization of the functionality. Okay, so this is why there is a huge variety in circuits. Okay, as I explained earlier, when this current source I0 is connected to the source of the transistor, the source voltage adjusts itself such that in steady state the current flowing in the transistor equals I0. Okay, and this VGS will be adjusted to whatever is required to have a value of I0. So VGS to carry a current of I0 is the threshold voltage Vt plus square root of 2 times I0 by mu n Cox W by L. So the source voltage here is this fixed voltage VG0 at the gate minus VGS, which is VG0 minus VT minus square root 2I0 by mu n Cox W by L. Okay. So eventually the source voltage reaches the correct voltage. Okay.